Well, it's time for us to have a conversation about stress and strain. And you're all familiar with stress. You've probably had moments where you suffered from academic stress. Hopefully, this isn't one of those moments. Strain, you may have had a strained relationship at some point in your life. The way we use the term stress and strain in everyday life are different than the way we use the term stress and strain in our study of physics. So I'm more interested in these types of stress and strain. One type of stress we might study is the stress in a guitar string. So a guitar string, as you tune it, you can produce a higher pitch as you make the string tighter. So the tension in the guitar string is a form of stress. Now the question is, how much longer does that string become as the tension is applied? So maybe if we drew a picture of a relaxed guitar string, it would look like this, and then you apply tension, and because it's fixed down at this end and tightened over here at this end, the tension pulls in both directions across the length of the guitar string, and as a result, the string must become a little bit longer. So that's what we mean when we talk about strain. The stress is the tension. It's the attempt to deform the string. The strain is how much longer the string becomes. So if that's L naught, then this is some delta L, so that the final length of the string is L naught plus delta L. So the delta L is the resulting strain due to the stress known as tension. And the same thing, if you, if you gained weight, then would that add any additional stress to your femur bone? Or if you had somebody ride piggyback on your shoulders. That's a ridiculous picture, but you get the idea. Yeah, for sure. Instead of tension, this would be a case of compression. And compression is just another form of stress. And so in that case, if we modeled the femur, kind of like our guitar string has a cylinder, then there's a force of compression, and that causes the bone to become smaller. Now, it's not noticeable with the naked eye that the bone becomes shorter, but it actually physically does become a little bit shorter, and there's some change in the length, and that's the resulting strain on your bone. There's an upper limit to how much shorter the bone can become before it fractures. So we'll talk about the fracture point involved in stress to strain ratios. Another form of stress could be the additional fluid pressure when a ball is taken underwater. So we might refer to that as a bulk stress. And that bulk stress is due to additional fluid pressure. So tension is a force measured in newtons. Pressure is equal to a force per unit area. So the ball has a total surface area across it. Either way, pressure or force are words that can be substituted for stress. The strain in this case, well, if the ball was originally that large and it gets pushed in from all sides due to the increased fluid pressure, then it'll shrink in size. And so instead of a change in length, we'll have a change in volume as an expression of the strain when bulk stress is involved. So let me restate that clearly, what we mean when we talk about stress and strain. Let me give you some definitions you can copy into your notes. Did you catch the way I said it earlier? The stress is the attempt. It's your effort. Oh, we got that. It's your effort to try and deform some object. So it's either measured in newtons or pascals, where a pascal is equivalent to a newton expressed across 1 square meter of area, right? Yeah, exactly. Stress is expressed as either force or pressure, where pressure is the same thing as force per unit area. And that's it. Now, strain, on the other hand, is not the attempt to deform. It's not the amount of force or the amount of pressure. The strain is the outcome. The strain is the resulting amount of deformation. So strain is really either a displacement or a change in volume. So it's either measured in cubic meter, it's either measured in meters or cubic meters, right? It's either a change in length or it's a change in volume. So stress is the attempt to deform, strain is how much deformation you get. And we've actually already studied stress and strain a little bit. We studied Hooke's law. And remember, Hooke's law is the one that governs the behavior of springs. Actually, it governs the behavior of other materials that have a linear relationship between stress and strain, but springs are one of the best examples. So let's say a spring naturally, without any additional force applied to it, hangs with a length L naught, and then you attach some weight to the spring and the coils get farther apart, and now there's been an increase in the length. The new final length of the spring is L, so we're interested in the value of delta L. We might have expressed that before as delta X. Nothing wrong with pretending our x-axis points downward. So there's a force of gravity thanks to the hanging weight. And Hooke's law is the one that tells us that the value of delta X is in direct proportion to the amount of force, meaning if you put double the weight at the end of the spring, then it would have an increase in length that's twice as much as the original case. If you triple the weight, triple the change in length, and so on. So Hooke's law says the force exerted by a spring is equal to negative K times delta X. Well, force is an expression of what? Stress, right? And delta X is a way of saying the resulting strain. Now, in magnitude, if we're just interested in the magnitude of the stress, then we can get rid of the negative sign in our expression for Hooke's law. And so we rearrange, we solve for K, and we find K is just a ratio of stress divided by strain. We called it spring stiffness, but we could also say the K value of the spring is a stress to strain ratio, and it's a constant. Well, not really. It's only a constant within a particular range. If you do hang a greater amount of weight, then the spring might stretch this far. Well, there's an upper limit to how much mass or how much weight you can hang from the end of the spring and still expect it to have this linear relationship between force and displacement. In fact, at some point, you can stretch it so far that it doesn't return to its original shape. So this doesn't just apply to springs. This relationship between stress and strain and the fact that the stress to strain ratio may be constant within a particular range applies to materials like steel. So back to the guitar string, if the strings are made out of steel, then the relationship between the amount of tension and the increase in length just has a direct linear proportionality as long as you don't put too much tension into the string. As long as you stay within what we call the proportional limit, then the force compared to the change in length is a constant stress-strain ratio. What else other than steel? Well, bone, right? We talked about compressing a femur, rock, glass, cardboard. So a material doesn't have to be easily stretched or compressed like a spring in order to have elastic behavior. A spring is just a material with a very large elastic limit. So we recognize the springiness of a spring. We don't recognize the springiness of steel or bone or rock or glass. But they all have a springiness to them, just meaning that they have some sort of a relationship between force and displacement, or between stress and strain. So we should picture this graphically. Let's say this represents the amount of stress in your femur bone. So as more and more weight piles on your shoulders, then an increasing amount of stress or an increasing amount of force shows up in the bone. Actually, let's think of it like this. Let's model the femur. And that's not too far off. It's mainly cylindrical in shape. So when some force is impressed downward on the bone, it's going to have a compression, and so there's a change in length. How about this? Let's compare the force to the amount of cross-sectional area, because I'm going to imagine somebody with sturdy, larger bones can handle a greater load than somebody with skinnier bones, right? And so it's not just the force we're concerned with, it's the ratio of force compared to the cross-sectional area. So we'll measure the stress that way. We'll say, instead of force, we'll talk about the force per unit area for the bone. But in either case, that would be a way of describing the stress. And if we graph the stress compared to the strain, where the strain is measured in meters, we'll get a shape of graph that looks something like this. Now let's describe what's going on in all these points. Well, I'm going to refer to this as point A, B, C, and D, and try to explain why those are important points on this graph of stress versus strain. So you can see from the origin up to point A, the shape is a straight line. So if you applied, well, 1 unit of stress, then that might lead to 1 unit of strain. If you double the amount of stress, then what's the result? Then it's double the amount of strain. Triple the stress, triple the strain. It's a linear relationship. And that's just a way of saying that in this region, from 0 up to A, the ratio of stress divided by strain is a constant value. That'd be like saying try to find the slope of this line segment. Well, you could pick any point. You could pick that point and measure what? Rise over run. And if instead you wanted to pick this point, now that's more stress, but it's also that much more strain, and so your calculation of rise over run would still give you the same value. So that's what we're going to refer to this. From 0 to A, we're going to call this the proportional limit, meaning there's a direct proportionality between stress and strain for that portion of the graph. For any real material, if you provide additional stress beyond the proportional limit, then a greater amount of stress, so we stress it all the way up to this data point, then for sure that leads to a greater amount of strain, but it's nonlinear. You can see the graph starts to curve. And so if it's nonlinear, there's no longer a direct proportionality. So from the origin up to point B, that doesn't represent a proportional limit, but it does represent another limit. If you continue to stress it and stress, now if you start to remove the stress, if you start to take weight off of the bone and make the force smaller and smaller, and you record data points for the change in length or the resulting strain as you de-stress the material, you just get the same set of data points as you reverse the load. And so the object will return to its original length when the stress is fully removed. As long as that's the case, you've remained within what we call the elastic limit for the material. So we can make a dividing line on this graph that goes up to the elastic limit, and then we can say this is all the elastic range for the material that's being stressed out. So something interesting happens if you increase the force beyond the elastic limit. So you provide an amount of stress up to this point. Then, once again, you get a greater amount of strain as a result. But now if you were to start to back off the stress and collect data points going in reverse, you wouldn't get the same set of data points. You get data points that lead to a curve like this as the stress is taken away. Meaning, when the stress or the force comes all the way back to 0, it doesn't bring you back to 0 amount of strain. The curve, as the stress is removed, zero stress leads to a non-zero amount of strain in the end. And so this is what's happened. If you ever owned a slinky, then chances are you owned a broken slinky. You stretched it so far that when you took the stress away, the coils didn't come back to touching. They had what we call a permanent set. So we refer to that type of behavior as plastic behavior. So the elastic range is the range for which you can stress something and expect it to return to its original length. But once you go past point B on this graph, then you get into plastic behavior, or the plastic range. And it might even go something like this. If you want to create even more strain than this point, then you've got to provide even more stress. If I want to get this much strain, I need now this much stress. And on you might find that you can get an increase in the amount of strain even if you back off the stress. If you continue to pull or push on the material, whether it's a tension or compression problem, if you continue to provide some non-zero amount of stress, you might find that you can back off the stress and still get a continuation in the increase of the strain. And you've maybe noticed that if you ever pulled taffy before. If you have a bar of taffy, or maybe really soft licorice, or something like this, right? When you first pull it, it's pretty rigid, and the relationship of stress to strain would be a large constant value, and then you pull it. Now, taffy is like the opposite of a spring. It has a very small portion of this graph. So no two graphs are going to be the same in length, but they will have the same shape. So for example, for taffy, you might get that the proportional limit is very short, and then after that there's a very small addition within the elastic limit, but then the plastic range might extend on and on and on really far, right? Whereas a spring gives you a graph like this. The proportional range goes on for a long time, and even the elastic range goes on for a long time. But once you go beyond the elastic limit, that plasticity doesn't go on for very long, and if you pull too far, then the material just breaks. Whereas for taffy, once you enter the plastic limit, you can pull and pull and pull and pull, and it takes a long time before you reach the fracture point. So that's what point D represents. That's just the fracture point. That's the point at which you've reached the greatest amount of strain you'll ever possibly get before the material just breaks. And so have you ever felt that with taffy? You pull it and you pull it and you pull it, and as it gets longer, the amount of force required to make it go even longer still becomes even less. So that's the nature of the negative slope from point C up to point D. So we need to study this in greater detail. We need to study some sort of formula or quantity, or give you an idea of how we can relate the stress to strain ratio for things like guitar strings and femurs, bone and steel. So whether you're attempting to stretch or you're attempting to compress, whether it's tension or compression, if the material involved has a large value of length and a relatively smaller value for cross-sectional area, then the stress to strain ratio has a name for it. We call that, well, the symbol for it is capital Y, and it stands for a value known as Young's modulus. So Young's modulus for a guitar string or a bone is sort of like the K value for a spring. It's just that constant value of stress to strain ratio as long as you stay within the proportional limit. So that's what our study is about. We're going to study materials that stay within their proportional limit so we can express the stress to strain ratio as some sort of constant value. For the ball, the inflated ball that was taken underwater, then the resulting strain is measured as a change in volume. Well, in that case, we give a different name to the stress to strain ratio. It's still a constant as long as we stay within the proportional limit, but the name we give for this is, the symbol anyway, is capital B, and that stands for the bulk modulus. We'll also go deeper into investigation of what we call the shear modulus, and that would be the case of a material that is neither stretched. See, these forces that pull in opposite directions at least align with each other through the center of mass of the material, or when a bone is compressed, these forces align with each other and pass through the center of mass of the material. But there are some cases where we might take an object and apply a force to the right at the top and a force to the left at the bottom. The forces don't align through the center of mass, and the resulting deformation, maybe the object is anchored at this corner, makes the object look like this. And so when forces are applied in opposing directions but they don't line up with each other, we say that a shear force has been applied. So stay tuned for further lessons on Young's modulus, bulk modulus, and shear modulus for different materials that are stressed within their proportional limits.